Hello friends, welcome to follow up. In this video, we are going to analyze problem 1043, partition array for maximum sum. In this video, we are going to explain a solution based on dynamic programming. So first, we are going to quickly look at the problem statement, and then we do some simple observations, and finally we share the code. So here we are given an integer array called ARR or array. So we want to partition the array into contiguous subarrays of length at most k. After partitioning, each subarray has their values changed to become the maximum value of that subarray, right? So we want to return the largest sum of the given array after partitioning. The test cases are generated so that the answer fits in a 22-bit integer, right? So this last one actually is no special effect for our coding or for our solving the problem. So if you're not, you cannot digest the meaning of this one. So in practice, 32-bit integer means that the range of the integer, so basically is in 2 to the power -3. So for this one, that's the n equal to 2 to the power 31 minus 1. So the most significant bit is a sign bit. In other words, if you regard the leftmost is the most significant, this one actually corresponding to a sign. If it's 1, it's negative. If 0 is positive, right? So then you can do the summation, right? So you can do 2 to the power 0 plus some 2 to the power 1, and then plus 2 to the power, so up to 30. So 31 bit is 30, right? So this summation is nothing but 2 to the power 31 minus 1, right? So this gives the range roughly for this 32-bit integer, signed integer, right? So here it also requires, this is also greater than or equal to 0, right? Anyway, it's not very essential. So here we have 3 examples. The last example is very special, right? So k is 1, the length is also 1, so it returns the sum, and this also itself, right? So in the first example, so k equals 3, so you can contain at most 3 consecutive numbers in the partition. So here, for example, 15 is a global maximum for this array. So I want this contains as many neighbors as possible, right? So we have 1, 15, 7, right? So this one will, all the 3 numbers will change to be 15, right? You get here. And then we have none. So because here 10 is larger than none, so we have this 3. So it afterwards they will be changed to be 10. So you get 10, 10, 10, and none itself to be a subarray. So we get none. So if you add them together, you get 84. For example 2, actually this is a very interesting one. So the k is 4, right? So the output is 83. So here is observation. So the optimal partitions, optimal it means that corresponding to the largest output, are not unique. So we can use example 2 to demonstrate this point. So for example, if you do this partition, right, and then the first one contains 1, and the second one 4, 1, 5, 7, and the last one is 3, 6, 1, 9, 9, 3. But in the second partition, we can group 1 and 4 together. Well, we put 1, 5, 7, and another one, and the last 2 remain unchanged. So then you can see this one is corresponding to 1, and this corresponding to us 4 sevens, right? So this one is 4 nines, this one's 2 nines. But if you look at the 2 again, so this corresponds to 2 4s. You have 2 times 4, and here you have 3 sevens. Then 2 times 4 plus 3 7 is 29. So here 1 plus 7 times 4 is also 29. Therefore, the return for these 2 partitions are the same. In this regard, optimal partitions are not unique, right? So this is the one observation. The second observation is that we don't need to actually do a real partition to solve this problem. We can use dynamic programming. So here for this problem, if you don't have, this is a very suggestive DP problem. If you don't have the idea, so you can look at this, right? You have a hint, right? So I'm going to solve this problem following this hint, because it's very easy to explain from a pedagogical point of view, right? So now, before we make that, let me make some preparation. So here I'm going to use dpi to be the largest number we get if we use optimal partition or partitions, right? Because the unique non-uniqueness for array up to index I and inclusive, right? And then we just need to do dp update rule for I plus 1. So here you don't need to say I plus 1 or minus 1. You see I is the current one and I plus 1 is the next one, right? So update for next one, right? From dpi. And this way it will be very easy to solve this problem. So basically we just need to focus on key elements including the current one, right? So now let me write the code, and in between we're going to explain the logic. So there are many ways to write this code. Here first, let me write this n equals the length of this array. This is for nothing but for convenience. Then we initialize a dp table, right? So 0 times n, right? So dp0 or dp0 is very easy to set, because if you have a length 1, we assume that key is greater than or equal to 1, but less than or equal to the length for sure. So we're going to set it to be array 0, right? You can only put it together with itself, like example 3. And now we get this one. We just need to do dp update, right? So this is the initialization, right? So dp initialization. And then for dp update rule, so this is rather simple. We just try all the possibilities. So basically we have set for index 0. So for I in range 1 to n, right? So we want to set dpi, right? So now we look at this, element at index I, in other words, array I, right? So then we see that here we have array I. So then the previous one will be array I minus 1, right? Then we need to look at array I minus k plus 1. So those are key elements, right? Because we can group array I as itself, or together with this one, or together up to this one, right? There are key different possibilities, right? Then if we put array I itself together, right, what we are going to get is, so we want to see for d in range, say 1 minus k. That's first, if we put this array I itself together, so then the largest number we can return is nothing but dp I minus 1 plus array I, right? This is very simple. Here, because we start from 1 for the index I minus 1 is also always meaningful. And then we check the other k minus 1 possibilities, right? Then first, if I minus d equals 0, because after we checked up to this one, so we check, so each one is d minus 1, d is at most k, right? So if we want to look at, we have something like this, dp, we want in general dp I minus d plus max of array from I minus d plus 1 up to index I and inclusive, the maximum, and then check times the number of atoms, right? So this is because we want to return it to replace all the elements to the maximum, or you can see when we compute the return, we use the maximum element in the subarray, right? So if this is the case, so what we are going to do, we are dp is the maximal of the pre-state dpi, and then because this will have a 0, right? Then this 0 then this ID minus 1, right, actually. So what we have is dp max, say we have array, let's see, I minus d, right? Then up to I. Then the number of elements is nothing but 1 plus d, right? So this is nothing but the latter index, I plus 1, minus the previous index. So in this case, we cannot talk about d I minus d minus 1, right? Because in this case, this will be less than 0, right? So here the index is very important. So this is the one case. If I minus d minus 1 is greater than or equal to 0, so in this case, we can do the things correct. So here is I minus d, right? So what we are going to do is the general case. So dpi, the previous state, then dp I minus d minus 1, right? Then we do max array, see, I minus d up to I plus 1. Then you multiply the number of items, that is 1 plus d, right? So afterwards, we just need to return dp, the last element, negative 1. So here, let's first do a test, then we make some comments. Yeah, it passes one case, and then you can test generic case. Yeah, so here what I want to see is that when we write this one, we didn't do a lot of hard think. The reason is that when we do this one, it's very brute force. But you can try to improve this part. So overall, the time complexity will be n times k, right? So, but this problem gives us a very direct example for dynamic programming, right? So with that said, basically that's about it for this video or for this specific problem. If you would like to practice more problems related to dynamic programming, you can check out the dynamic programming playlist in our channel. With that said, I guess that's it for this video. Thank you for watching.